Before I start my talk, I wanted to address my good old friends and new friends and say something about the title, which says that I am affiliated both with the Department of Physics in NYU Abu Dhabi and also Strategy and Planning in Abu Dhabi Investment Authority. You know, there is a saying in the United States Army, once a Marine, always a Marine. And the same is true about people who spend some time in London Institute, like me and Khanin here. So whatever I do, wherever I do, physics is both in my genes and in my brain. So I'm, of course, a physicist, regardless what I do on the side. And I have many interests. But now I'm with you just as a physicist. So I'm going to skip the abstract because I'm going to talk about these issues. Let me start with the most important things. Here's quotations from Richard Feynman, who wrote half a century ago in his famous lecture on physics. And I will just read that quotation. There's a physical problem that's common to many fields, that is very old, and that has not been solved. It is not the problem of finding new fundamental particles, note that phrase, but something left over from a long time ago, over 100 years. Nobody in physics has really been able to analyze it mathematically satisfactorily, in spite of its importance for sister sciences. It is analysis of circulating or turbulent fluids. The two phrases I highlighted here, one is fundamental particles, another is circulating fluids. And that's exactly what I'm going to talk about. So the turbulence problem, it looks deceptively simple. Find the limit of solution of Navier-Stokes equation when viscosity goes to 0 at fixed energy flow into system. And here is Navier-Stokes equation, which everybody knows, including incompressibility. So in this limit, when viscosity goes to 0, you would be able to drop this term everywhere except regions with high Laplacian, which are some singular surfaces or singular lines. You could imagine something more sophisticated than that, but from the point of view of classical flows, you would have something like turbulent, boundary layer, which is a vortex sheet, and vortex line. They are known to exist. They were studied. So let's assume that Navier-Stokes equation turns to Euler equation everywhere except these singular regions. And these singular regions presumably are responsible for the dissipation. Now, the energy balance, let me remind you the energy balance, which I write in slightly unusual form. We find time derivative of the Hamiltonian, it adds up from two terms. There is dissipation, which I prefer to write as viscosity times entropy, and the energy, positive term is energy pumped from outside, and negative term is dissipation, so which is nu times entropy. And energy pumping, if you write dissipation as entropy, then energy pumping is integral, which contains, in addition to the velocity times enthalpy, it contains term which is V cross omega, which comes from transformation of square of strain into square of omega. The difference between square of strain and strain of square of vorticity is total gradient, and I included that gradient into the energy current. We are now interested in this first integral, integral of omega squared, and obviously, in order to have anomalous dissipation in the limit of viscosity going to 0, you will have to have a large omega in some region, and that integration, singular omega, would compensate the factor of nu in front. So these singular regions with infinite omega may lead to anomalous dissipation, a finite limit of the integral in dissipation energy at 0 viscosity. Indeed, such anomalous dissipation was present in analytic solution of the Navier-Stokes equations, pioneered by Burgers and generalized by Townsend. These solutions were found in 48 and 51. They were known for a long time and then forgotten by almost everybody. Anyway, for the vortex sheet, the solution is this. They both have the Gaussian, which tends to delta function. And in case of the sheet, it's the vorticity is tangent to the plane, but perpendicular to discontinuity of velocity, n cross delta v. And the width is square root of nu divided by transverse strain, Laplacian of the surface Laplacian of the potential in case of the sheet. In case of the tube, similar formula with Gaussian, which is tending to delta function in transverse plane. And again, width is square root of viscosity divided by transverse strain. And so delta V is velocity gap, gamma is velocity circulation in this formula, and Sij is background strain. It is not singular. Only rotational part of vorticity is singular. So this is well-known and well-forgotten formula, but it's very important in my view. Anomalous dissipation in singular regions was observed in dynamical simulations, and it's a known fact. And people are looking for these singular regions. But here are the problems, which was hopeful, I think clear. It was clear to Burgers that these are two problems. He didn't know how to solve them. First problem is to find matching Euler flow with singular vortex line. It's easier said than done. You really don't have a smooth solution, global solution of Euler flow with just a singular line and nothing else. That's not known. At least if you do it naively, you would get infinite energy, and that's not solution. So then second problem was to understand the nature of spontaneous stochastization. These two problems were not solved at the times of Burgers. And in fact, the whole microscopic turbulence theory got stuck in the middle of previous century. Most of the subsequent progress was phenomenological and numerical. There was a lot of understanding which were accrued since that time, but microscopic theory, starting from Navier-Stokes equation, got stuck. So we believe that we have found solution to both of these problems. And now I'm going to present this solution. So I don't have time to go through the whole steps of the trail leading to the summit, and I'll just fly over. And the longer version of my slides, I send them to the organizers, so they will be available for those who are curious, how did I arrive at these formulas in this picture. So here is the answers which I offer. Our theory offers quantitative answers to some lingering questions. So are there some fundamental particles in turbulence? This negative remark by Feynman was a prophecy. He subconsciously reminded us about fundamental particles. And he was right. He said no, but he subconsciously meant yes. Because there are quarks in turbulence. They are called Faddeev variables or spherical Clebsch fields. They are confined by unbroken gauge invariance, and their target space is unit sphere. So they don't, one cannot observe them in pure form as waves, but one can observe the vorticity strings as solitons of Clebsch field. So this field, Clebsch field, is prevented to be observed as a pure wave because of certain gauge invariance, which is not broken, just like quarks are not observable in QCD. But bound states, in this case, solitons made of these Clebsch fields, are observable, I claim. So here is how this soliton looks. So S is a unit vector in 3 dimensions, which is responds to the point on a 2-dimensional sphere S2. And there is an arbitrary factor, which we'll determine later, so that vorticity is Z times omega tilde, and velocity is Z times V tilde, and tilde corresponds to something which is purely made of this unit vector. So vorticity is a cross product of gradients of various components of this vector. That's a so-called topological current, which is identically conserved. I mean, divergence of omega always is 0 with this parameterization. And velocity is more complex. It's not local. So vorticity is expressed in terms of Clebsch variables locally, and velocity is non-local. It is related, there is some harmonic potential phi, and there is a potential part grad phi, and then there is a Biot-Savart integral, which we write as follows. It is curl of integral of omega divided by Coulomb kernel r minus r prime. So that is a solution of incompressibility equation and equation relating omega to v. So omega is expressed locally in terms of these variables, and velocity is expressed non-locally. And that's very important difference. That's why velocity, especially its potential part, and vorticity are very different variables in my theory. And one has some simple properties. Another has some random component because of accumulation of these Biot-Savart tails. And that I will talk about later. So this flow belongs to a certain topological class with infinite vorticity at closed line and the velocity gap at the surface bounded by this loop. And I will talk about this topology a lot because that's the most important thing. That's something new which was not known at the Bergerstein. So the field S maps our physical space except this continuity surface and two-dimensional and its boundary, which is line. So imagine our space and cut out an infinitesimal tube around the loop and some infinitesimally thin surface inside this loop. So it's like imagine child trampoline or children's play. So there is a surface and there is a boundary. And both of them are excluded from physical space because there is singularity. So the rest of physical space, the whole space, with exception of this surface and its boundary, are mapped onto the sphere. And such mapping is described by two winding numbers. And the mapping has a very simple geometrical meaning. The omega form, if you multiply omega by area element of some surface, that's what you do when you do Stokes theorem. So this omega form is area element in this two-dimensional sphere. So this field maps area vorticity form on a surface into the area element on the sphere. And these simple canonical variables, phi1 and phi2, are expressed in terms of the three-component vector as follows. Phi1 is z times 1 plus s3, z component of this Clebsch field, and phi2 is argument of s1 plus I s2. So these are two angles. Phi2 is basically this equatorial, how it's called, azimuthal angle. One of them is longitude, another is latitude. So its longitude is phi2 and phi1 is related to latitude. That's the Euler angles on the sphere. So two coordinates on a sphere. So the surface bounded by the loop is mapped into area inside the oriented curve on a sphere. By definition, we choose spatial infinity to be mapped at the south pole. Then if that's the sphere, then the surface is mapped on the green region below this line with some angle, which is arbitrary parameter, as we see later. So singularities on the surface and the loop in physical space arise because of phase gap in the this complex field, S1 plus IS2. This azimuthal angle is defined modulo 2 pi. So the point at the point at the sphere and the one which comes after full circle are identical, equivalent. However, if you make the infinitesimal gap between these two, you will see that in fact the point doesn't just smoothly go from one side to another, it makes full rotation. So the gradients are infinite, though the field is continuous. If you take a limit, you will see that the gradients are they're delta functions. And that's the delta functions which are involved in vorticity. They come about because of this rotation. So the whole field is continuous in a sphere, but there are singularities related to rapid rotation of the point on a sphere. You kind of jumped full rotation, and that leads to singularity. So when the point in there are two kinds of rotations. Let me show. When the point encircles the loop. So here is the loop. So when the point goes around the loop, that's one kind of rotation. Two cycles. There is an infinitesimal torus surrounding the loop. There are two cycles of the torus. One goes around, another goes along. So the one which goes around is the one responsible for the circulation of the vortex. And there is another one which is ordinary circulation when you go along the loop. So there are two different circulations. Now, in the at the loop, in the vicinity of the loop, to get the finite circulation, which is needed by Berger's, I want to match that singular loop with the Berger's solution in the tangent direction of the loop. So when you look at the loop with magnifying glass, it's like a straight cylinder, and there is a very small width of that cylinder, and there is a circulation around that loop. That means the velocity diverges as this circulation divided by 2 pi r. And that basically matches the Berger's solution. Now, the field phi 3 doesn't have any singularities. It takes constant value on the loop, and that's my parameter to be obtained from the Hamiltonian. Now, the calculations of circulations are simple. It's because it's areas of the point on a sphere. That's a trivial geometric calculation. So there is alpha cycle, which is cycle around the loop, big cycle, and that is 2 pi times some integer m times 1 plus cosine lambda. Integer is a topological winding number. When the point goes along the loop, the corresponding image in collapsed space goes m times around the loop. And in the same way, when the point goes in transverse direction surrounding, encircling the loop at some point, again, the point on the target space goes L times around the sphere. So there are two winding numbers, M and L. Now, velocity gap is related to the gradient of S3 at some point on the surface. Because there's an angular gap, then you will get gradient of the S3 times this angular gap. So this angular gap, 2 pi L, it determines the velocity gap. So that's quite interesting singular field. From the point of view of velocity, it is singular. It has 1 over rho pole on the circle and velocity gap on a surface surrounded by a circle. But in terms of the basic variables, fundamental variables, collapse, it's totally continuous and just have some cycles around some loop, and that's it. And that's very important because of that property, we have finite energy. Now we surround the loop C by toroidal tube, and here are some trivial notations about the tangent vector T to the loop at some point, normal related to curvature of the loop, normal directed inwards, and the sigma, which is a third vector orthogonal both to the surface and the loop. So there is a frame. T and sigma is a coordinate frame associated with the point at the loop. Now, I'm now describing how the field phi 2, this angular field, how it behaves in the vicinity of the point of the loop. So it's very simple. It is related to the angle along the loop, which is 2 pi times s. S is parameter on the loop. So 2 pi s is the angle. And it's sometimes the integer m. And then there is another integer multiplying another angle beta, which is angle surrounding the little torus. So that's the singular behavior in a sense that it the point rapidly rotates around the pole, but it is always finite. It's not like it is. It cannot be infinite because it's on a sphere. All it can do is rapidly move around the sphere. And so that's an image of the torr. That's basically the flow around this infinitesimal loop. It spirals. There is a longitudinal component of velocity and rotational component of velocity. And of course, such a motion has helicity, and we'll discuss it shortly. So the local limit of the Burger's vortex is a delta function in the plane normal to the local direction of the loop. And here is a global formula generalizing this delta function. Very nice answer. This is the continuum limit of the Burger's vortex. Integral along the loop of three-dimensional delta function. Now, you know, at any point, the longitudinal integration removes one of the three delta functions, and you get two-dimensional delta function, which is Burger's answer. So this is a covariant form of the Burger's vortex, vorticity of the Burger's vortex in a continuum limit, in the Euler limit. So circulation gamma in our case is constant, doesn't vary along the loop. And this is an interesting thing. It's a consequence of the Euler equation for the Clebsch field. You see, Clebsch field, it is known fact. Any Clebsch field, regardless whether it's on a sphere or on a plane, is just passively advected by the flow. And in particular, it is passively advected along the loop. And that means that there is equation V grad S 3 equals 0. And since we expect the velocity at the loop to be tangent, any incompressible fluid at the boundary of its discontinuity has a velocity directed along the loop, along the boundary, because there is no flow outside. And that means that this C3 is constant around the loop. It's constant. And if C3 is constant, that means we have a finite area inside on a sphere, because this S3 is not an arbitrary curve, but just a constant curve of fixed angle. So therefore, we can take gamma beta out of the loop integral, and then we can find the helicity. Helicity is integral of V dot omega. So omega is integral with delta function. Delta function removes one of this integration. Gamma is taken out of the loop integral, and we get extremely simple answer. Helicity, contribution to helicity from the loop is just product of two gammas. So it is product of two winding numbers. Now there is also contribution to helicity from the surface, and I'll skip that calculation. There is similar calculation because there is a vortex sheet with discontinuity, and then there is also some contribution from the surface. Now there is no contribution from the remaining volume, and that is well-known fact. It is known that helicity is zero unless there is if the space is total complete R3, there is no helicity. It usually comes from infinity if you make a space three-dimensional sphere. But in our case, there is singularity at the loop and the surface, so there is another mechanism of helicity. But contribution from the remaining space R3 divided by S. Contribution from remaining space, if you substitute V and omega, you'll easily find that it is reduces to the following integral, which is 0 because phi1 is constant along the loop. So it's, in general, it is phi3 d phi1, but phi1 is constant, so we get 0. So that vanishes. So there is helicity for our column is purely anomalous. It comes from the surface and from the loop. But it's nice finite formula. Now, the most interesting part. I want everybody who is asleep because of my monotonous voice to wake up, because now I'm giving you the most important part. What is the Euler Hamiltonian? You have to take square of velocity and integrate over all space. Now, our space is Euler space, which is space except this little tube and thin surface, and contribution from inside of the tube and the surface. So inside, you take the full Navier-Stokes. My philosophy is that Euler is a limit of Navier-Stokes when the viscosity goes to 0. Or if you say it's not Euler, finally, it's not Euler. The turbulence theory is a limit of Navier-Stokes at viscosity going to 0. So what's the Hamiltonian of the turbulence theory? It's Euler Hamiltonian for the outside plus contribution from inside. Now, you could actually compute that contribution. You could match the Berger's vortex and this Calvinon vortex. You could match them at the surface of the tube, find relation between Berger's circulation and my circulation. And when you do that, you obtain the following result. So the Hamiltonian, which I get up to the factor z squared, is integral of v squared over the Euler region plus anomalous contribution. And that is the new term in the Hamiltonian, which would totally change the dynamics. This term involves this unknown parameter lambda, which is value of the Euler angle at the loop. And then there is very specific integral along the loop, which involves the logarithm of the component of the strain. Now, this r, you tend to 0. You can prove that in the limit when r goes to 0, this term, if you find the derivative with respect to r, you'll find the derivative of the first term, cancel the derivative of the second term, which means that the sum of these terms doesn't depend on r. In the limit when r goes to 0, I computed that, it is universal limit. So here is very specific Hamiltonian. It is totally irreversible because it has logarithm of strain, and strain is a time-odd quantity. When I make time reversal, strain changes sign. So this Hamiltonian could only exist for positive strain at the loop. So that's a condition of this solution. So the strain must be positive. And that's the origin of irreversibility, because what happens is if such solution is, some trial state arises, if it has negative strain, it will not be stable. This minimum, which is stable solution, implies positive strain. Or you may put it this way, the loop will automatically go along the region of the positive strain. I may say it this way. But anyway, if you fix the loop, then the strain must be positive. Is there something? Okay. So that is the most important thing. There is a Hamiltonian of the Navier-Stokes theory in the limit when viscosity goes to 0, and it differs from the Euler Hamiltonian, but very explicit anomalous term, which changes the whole story. And we'll see now how it changes the whole story. There are two scales involved in this Hamiltonian. One scale is the size of the loop, which explicitly enters our equation. But there is another scale hidden inside the logarithmic term. And that's the vortex core radius, which is related to the z and nu, etc. Now, this scale is much smaller than the size of the loop. Viscosity goes to 0. You have very thin loop, very large and thin loop, but you cannot set viscosity 0 because there are still logarithms. Logarithm in foreseeable future, even maybe 100 years later, will still be not an infinite number in any experiment or numerical experiment. So it is something which you cannot tend to infinity for any practical reason. Though theoretically, you might imagine what is the limit of the theory when viscosity really goes to 0. But that limit is way, way ahead of us. We are now talking about a situation when all power-like corrections from viscosity can be neglected, but logarithmic corrections are still there. Like asymptotic freedom in quark theory, similar situation. It's actually very much similar, as you will see later. So our free parameter is Z, and that describes our solution in the whole volume. We selected one specific Kelvinon, one specific singular solution. But if there's infinite volume where we have our turbulence, it is filled by all kinds of vortice structures. And you would think that if the structures which is able to dissipate is this singular vortex loop or string, so we have something like string theory. We have a gas, ideal gas of little closed strings. This generalization of idea of Onsager of ideal gas of point particles in 2 dimensions. In 3 dimensions, analogous topological objects will be closed string, closed ring made of vorticity. So that is our picture of the whole fluid. And then the energy balance, of course, only holds for the whole fluid. And any stationary solution of Navier-Stokes equation relates this parameter Z to the energy, total energy flow for whole system. So total energy flow, epsilon tot. If you take cube of that equation, you will see that epsilon tot is Z times sigma, Z cubed times sigma, and sigma is this. So we could find this sigma is determined from the condition of the conservation of energy. So it's parameter of the Euler theory, which is not specified in Euler theory. It's arbitrary within Euler theory. We can prove that it's an integral of motion. That's a well-known fact. So this integral of motion of Euler theory at the higher level, when we consider Euler theory as a limit of the Navier-Stokes viscosity going to 0, you'll see that for that Navier-Stokes theory to be consistent, to have conserved energy, you actually have relation for involving this Z and the energy pumped from outside forces into the system. And that is this relation. And that's very important. So the Z, which was in the old-fashioned Euler theories, was constant.
I have a quick question. I mean,
louder, please.
I have a microphone here. I mean, I don't know what is actually following or what is an assumption. Your assumption is there are these vortex tubes. Inside the vortex tubes, you will use the Berger's solution. And then
let me explain. There are 2 scales. At the scale of the distance about the size of the loop, it's pure Euler singular line. This singularity is resolved. If you take a magnifying glass and look at this loop, it's in fact very, very thin tube. It has a thickness related to viscosity. And that is the Berger solution indeed has a...
No, I understand. But this is your assumption about the flow, that all flows can be broken up into such objects.
Well, let me put it this way. I'm looking for the fixed point of the Hopf equation for the probability. I just skipped that part. So I'm finding a specific fixed point. My specific fixed point is a Euler solution everywhere except singular domain, and where it is matching, where it matches the Berger's vortex. And I don't have to make assumptions. There is unique relation between Berger's and Euler. My solution has to match Berger's, and that's how I find all parameters. Now, it is specific solution for turbulence. If somebody finds another one, let's consider that one.
So the other question I had was, you said in the same sentence, energy conservation and Navier-Stokes.
Yes, let me explain.
Okay.
If you have stationary solution of Navier-Stokes, time derivative of any function of that solution is 0 by definition of what is stationary solution. So time derivative of Hamiltonian is identically 0 on the stationary solution. But if you look how this 0 is achieved, you will see that there is a minus contribution, which is integral of dissipation, plus positive contribution, which is the boundary term, the flow from the bound. If you would consider a periodic cube, you would not have it. But if you have a actually huge sphere with a boundary, you'll find out that the energy derivative is 0, and it is minus, the 0 equals minus dissipation plus flow from the outside world.
Stokes you're talking about?
Hmm?
It's really a forced Navier-Stokes, which is statistical.
No. Let other people play with auxiliary parameters. I am solving Navier-Stokes.
Okay,
I don't have no.
fine. We'll discuss it later. It's getting too
I
close.
don't have external forces.
Okay, thank you.
I say Navier-Stokes, I mean Navier-Stokes, but there are boundaries, and from the boundary you could there could energy flow. Like if the ship moves in the sea, for the outside world, there is no random forces. It's just the ship on the boundary of the turbulence volume, which is shaking it. So you don't need random forces if you find internal randomness, which I will do soon. Yes. Did I say 3 torus? I said 2 torus. It's a tube, like a, around this line, yes. Yes, I have, actually it's not a torus, it's donut. It's what is inside the torus, yes. No, I didn't say that. No, you got me wrong. Excuse me, you got me wrong. Let me answer a question. Let me answer. Okay. So to answer a question, I have 3-dimensional space. Then there is 1-dimensional line. I surround this 1-dimensional line by 2-dimensional torus. Inside this torus, there is a region where Euler don't apply. So Euler applies to the region outside of that 2-dimensional torus, and Burgers applies inside this region of 2 dimensions. I don't have time to answer that question. Excuse me. Let's talk later. We will discuss it later after this talk. So here is important thing. This parameter z is just an overall constant depending on the whole volume. Imagine the ideal gas full of little closed strings. So z is common global parameter for the whole solution, and it is related to the total energy flow into that volume and related to dissipation in each of these, sum of dissipations in each of these little rings. So z doesn't depend on my particular loop, which I'm considering. And then my Reynolds number is ratio of z to nu. Z has dimension of viscosity. And ratio of z to nu is Reynolds number. You could relate it to the average size of these kelvinons and their number in the whole volume. So it's, if you divide E total by the number, presumably the number is proportional to volume, total energy is also proportional to volume, the ratio is finite, and then there is average size of kelvinon, and that's the estimate of this z. It doesn't depend on my particular kelvinon, it depends on others, on the whole set. So it could be quite large, but still logarithm cannot be considered as large number. Here is, let's discuss another important point. The appearance of logarithm in the Hamiltonian signifies the breaking of scale invariant. Logarithm is not scale invariant object. It additively translates it when you make a scale transformation. And we have logarithm of local curvature divided by the thickness of the Burgers vortex. So it is finite parameter. This logarithmic breaking of scale invariance resembles what we have in quantum chromodynamics. And there you could still consider it large parameter and solve what is called leading logs. And that leads to modification of the multifractal scaling laws. So what is called Z2 of n, in fact, would be dependent on scale. if you consider zeta as logarithmic derivative of moment, nth moment over the scale, you will find that this logarithmic derivative is not really constant, but slightly depends on logarithm of scale. And that, of course, would not be detected in DNS, where for all practical purposes, logarithm is a constant. So if I will give the answer and DNS, people making DNS will start looking for, they'll probably find better fit, which is not fitting this zeta as constant, but would introduce some running dependence of logarithm, and I hope that they will find the correction I predict. Let's talk about that. So let me skip this part because that's not important. So we have ideal gas of vortex strings. And here is another important thing in this ideal gas. There is a small background velocity. How we get this small background velocity? Here is how. You have the total velocity field is sum of all contributions, not from this particular candelon where we consider the velocity, but also from all others in the whole space. And this contribution is a well-known Biot-Savart integral, and that decays with distance as 1 over r to the cube. So it slowly decays with distance, like 1 over r to the cube. But the number of existing remote Kelvinons is proportional to r cube. So we have something like, it's called night sky paradox. Contribution is 1 over r cubed multiplied by r squared dr, which is a number of objects, shining objects in a spherical layer, and you will get something large. So you will get large number of small terms, and each term is independently random because each of these little loops and their locations are random. They don't interact with each other. They are results of some random initial conditions. So at any given point in space, you will have sum of random terms, large number of small random terms. Doesn't it sound familiar? Yes, it is central limit theorem. That will provide this Gaussian background vector field. So there will be small, presumably, Gaussian background velocity. And that, of course, was observed. People indeed measured distribution of local velocity in turbulence. It's pure, boring Gaussian, as if there is nothing like multifractality or whatever. Intermittence is just Gaussian distribution. Because I see a simple explanation, because it's contribution from tails of vorticity structures all over the space. And that's by central limit theorem is Gaussian. Unlike vorticity, which is local. Vorticity is concentrated in small lumps, and so is circulation, but velocity is totally different. Contribution from the global contribution from the whole gas. That's why it is constant and Gaussian. So, what? I will average. Here's the philosophy. I have a fixed point, which is at any given place, it is a specific realization of that large number, a random number, right? At another space will be another realization. And of course, I will average, I will postpone this averaging. I will compute my solution. I'll find observable like circulation. And then at the end, I will average of Gaussian distribution, and that will give me statistics. So my statistics comes because of that average. At any given point in space, it is fixed number. Move to another place, it's another number. If you average over volume, you will get effectively averaging over Gaussian. So yes, it is, but I don't have time. You see, it is a fixed snapshot. At any fixed snapshot, it is, of course, specific realization of Gauss of numbers. But if I go all over the volume, I will effectively average over these realizations, and that is the Gaussian integral, which I can always define later. So at any instant, let's say local place in space, it's a fixed random number. And the reason for that is because there are zero modes. These locations of other Kelvinons in their directions are zero modes. The Hamiltonian doesn't depend on them. If they're very far away, our Hamiltonian is invariant with respect to translation and rotation. The only influence on each other is because of the tails. So if you neglect the tails, if you consider that's an ideal gas very far away, it is a degenerate system. That's the origin of randomness. You have a degenerate system, then your parameters of the system in the fixed point in steady state are random. You simply go over space and you will effectively get averaging over these random numbers. I believe that's very important. I think people noticed that before, but in my view, that is the mechanism of spontaneous stochastization. These, long tails of contribution to velocity from various vortex structures. So now this random Gaussian velocity would, of course, influence my Kelvinon. It's small, but it will influence. Now, in the zero approximation, it will not influence because it's just global shift and neither vorticity, neither circulation nor anything depends on constant velocity. However, in next order over this small velocity, there will be contribution. Why? Because this velocity shifts the boundary condition. I have the boundary condition that normal derivative on the surface equals zero. So normal velocity. So normal velocity is now shifted by some constant thing, and then you will have shift in boundary conditions. So in second order on this external small velocity, I will have contribution to my solution when I minimize. And that contribution I couldn't find. That's a problem which I don't know how to solve yet. But all I can say is that it is going to be some quadratic form in terms of this Gaussian velocity. Some unknown quadratic form Q, just this 3 by 3 constant matrix. So that will shift our parameter lambda. This parameter lambda is the only parameter which enters our expressions for circulation. So gamma will be 1 plus cos lambda minus this shift. And here is the beautiful part. So when we do these calculations, you will say you will get in this approximation Gaussian distribution plus some quadratic term, and that's a calculable probability. And that is the Wilson loop, square of determinant of the resulting matrix of quadratic form. So 1 comes from the Gaussian distribution of velocities, and this lambda comes from this extra term. So that's characteristic function for the probability of circulation. So there is very simple algebraic formula, which is ridiculously simple, cannot be true. But there is complexity, which is hidden in how these objects depend on the shape of the loop. And to find that, you'll have to really solve minimization of that Hamiltonian. Now you may ask, how do I know that this Hamiltonian has a minimum? Because of topological reasons. I fixed the dissipation, and that's related to the circulation, and therefore it couldn't be zero. So this Hamiltonian, by definition, with my normalization of the parameter z, the Hamiltonian doesn't have a minimum at zero. That's topology. Solution with certain topological class, and though I cannot find it, but I think prove, for a physicist, not for a mathematician, I can prove that within this class, zero is not solution. Now, here is the remarkably simple answer for the probability for circulation. It's an integral of the Gaussian vector psi, and there is delta function which expresses circulation in terms of some constant plus quadratic formula of psi. So what happens when if we want to have gamma very large positive? That means that one of the components of this vector psi should be large. And that is component corresponding to the largest eigenvalue of lambda. And when you compute that integral, you will get a very simple result. I will skip that part. Here is the result you will get. It's exponential of gamma. divided by square root of gamma. I think I'm showing the, I think these are, hold on, I think I'm showing the, hold on. I'm showing you the wrong. So here is the comparison of this distribution with the experimental data. So at the x-axis is the value of circulation in units of viscosity. At the y-axis is logarithm of this quantity, logarithm of probability times square root. I claim it is linear function of gamma after you multiply by square root. And that is fitting ridiculously well. It is practically within the statistical errors. And these are results of the probability computed in DNS by Srinivasan and his team. It was for 8K cube, and that is the best data I got my hands on, and it fits this data perfectly. Now, with negative gamma, it's still very good, but it's less perfect. There are small deviations. So there is something happening at small gamma where the theory doesn't apply, because the theory only applies at large gamma. Remember that my Reynolds number is ratio over gamma to viscosity. So on x-axis, in fact, my Reynolds number. So let me kind of summarize my talk. If I have a few more minutes, I need 5 minutes. So are there some fundamental particles? Yes. And they are, what is a big picture? It's an ideal gas of closed strings, 3D, which is a 3D extension of ideal gas of point vortices advocated by Onzager. And each string represents a singular line vortex. And the Clebsch field surrounding monopole ring is a soliton, mapping the physical space into sphere. And normalization of this Z is related to energy flow. And that's why, though it has viscosity of dimensions of viscosity, it is finite, and viscosity going to 0. What makes turbulence irreversible? For arbitrary small viscosity, there are irreversible anomalous contributions to all observables from the singular line of the Kelvinon vortex, regularized by Berger's vortex at the core. So we computed these anomalous terms for Hamiltonian, helicity, and energy dissipation. With these terms, Hamiltonian dynamics applies to the theory of strong turbulence. Euler dynamics doesn't, but with these anomalous terms, it is the limit of Navier-Stokes when viscosity going to 0. Hamiltonian dynamics responding to that limit. Now, what is anomalous dissipation? It's integral of square of circulation over longitudinal component of strain. It's not like qualitative, discussions about existence of the anomalous dissipation. It's equation where there is a left side and the right side. It's not like right side is something transformation of the left side. The right side is an expected formula relating other observables. So that's what's the difference between this and what we all tried before, where we understood, of course, there is anomalous dissipation, but here is a formula for it. Now, anomalous Hamiltonian, I already showed you. It's integral of v squared, regularized by some terms with very specific under logarithm. There is, again, the same longitudinal component of strain. So, and there is the factor of z, which can be dropped, but the rest is depending on the dynamical variable. So is there exact formula for Kelvinon field minimizing We don't know yet. More analytical and numerical work is required. So in appendix to this talk which I submitted to the organizer of the conference, you could read it, I hope, later. I have an example of the Clebsch field. I don't have exact solution, but I wrote example of totally non-singular Clebsch field with this topology, arbitrary number M and L. So it could be smooth. I present example when it is satisfying all the properties and is smooth. And you could use this initial data. This example can be used as initial data, and you could find the Hamiltonian by relaxation method like the one described yesterday in the talk. When you have some initial, then you iterate, do time dynamics, and make it converge to the minimum. I need 1 more minute. What's the origin of randomness? In our turbulence scenario, the Kelvinons arise spontaneously as the outlets of anomalous dissipation of the energy pumped into the flow. Locations and orientations, not shapes, of the singular strings are zero modes of a total Hamiltonian. So I already talked about that. What are the values of the winding numbers? They are random, but integers for topological reasons. They could be different in different regions of the infinite volume. Statistical averaging would involve the volume average, leading to a sum over topological classes. So just like in quantum mechanics, we have to sum over topological or statistical mechanics. We have to sum over topological classes. Here it arises when you integrate over the whole volume, because in different places of the volume, there could be different spontaneous solutions with these singular lines. Therefore, you have to sum over topological classes. In particular, a solution with minus M minus L will enter along with ML in this sum. And that doesn't make the time reversal, that doesn't make the time reversal go away, because Hamiltonian specifically is violating time reversal. Skip this. Yes, here is something I wanted to show you guys. How do we explain multifractals? Do we have a replacement for multifractals? Well, we don't have strict scaling laws with any multifractal indices because our Hamiltonian involves logarithmal scale. When properly summed up, like in a asymptotically free QCD, the logarithms may imitate anomalous dimensions with a running coupling constant. And we could make the same estimate. There is parameter lambda, which I skipped that part, but it has to be close to pi because there is 1 plus cosine lambda multiplying logarithm of Reynolds number. To better say, it's 1 plus cosine lambda squared times logarithm. So to make various terms in Hamiltonian balance each other, we have the following estimate: that sine lambda is logarithm of the size to the -1/4. That follows from rough estimate of minimization of the Hamiltonian. So if you take this formula and find logarithmic derivative, you'll find the K41 term, which just follows from dimension counting, minus correction. So there will be something below that famous Kolmogorov line, which for vorticity, for circulation, Kolmogorov line is not 1/3 n, but 4/3 n. So there will be some correction slowly depending on scale. And if people would know what to look for, they maybe will find it. But if they will simply naively fit the logarithmic derivative by a constant, they will not notice. They will take average value of that term, and that will mean some anomalous dimension. So in our theory, at least, anomalous dimensions come as asymptotic freedom. So they are, in fact, these anomalous dimensions are functions of logarithm scale, and they can be expanded in inverse powers of a logarithm scale. Just like in QCD, same thing. Philosophically, it is indeed anomalous dimensions. As much as in QCD, there is indeed approximate scale invariance and formal invariance. It's just violated by logarithms, and they, in the zero approximation, they just imitate the anomalous dimensions. But if you look closer, they are slightly running. And that is basically it? Oh, yes, one comment. There were lots of speculations in the past that helicity is the cause of anomalous dissipation. Not like that in our theory. Both dissipation and helicity are caused by same singular flow. It has topological properties. One of them is helicity, another is dynamical property, dissipation. So they are both caused by something else, but fluctuations of helicity are not relevant for the dissipation. That's it. Thank you very much.